Welcome to topic 8.6, Gauss's law, daily video number 3. In this video, we will apply Gauss's law to cylindrically symmetric examples. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Let's do a brief little warm-up here with a conducting cylinder. So if we look at the interior we have a long conducting cylinder with radius r, has a constant surface charge density of sigma. I want to know the magnitude of the electric field for less than r and greater than r. You're going to notice a theme throughout this entire video that we're always going to be checking what's going on inside and then outside. So just kind of be ready for that. So what's it going to be inside for a conducting cylinder? Yeah, 0. We got that one by now because all the charge resides on the surface in electrostatic equilibrium. So there's not going to be any charge located inside. Well, on the outside, what do we have to do for that one? That's what we're going to do next. But sure enough, our charge enclosed is going to be 0. And if it's 0, 0, we're going to get our 0 electric field. Okay, fine. Let's do the hard part. When it's on the outside, when it's on the exterior of this loop, this is what our Gaussian cylinder would look like. Notice or remember again that nothing's going through the end caps of the Gaussian cylinder. It's only going through the sides of it, as we can see down here as I kind of head on do. So this time, our left side, which is the easy side of the equation, is going to be 2 pi r, our circumference of our Gaussian cylinder, times our length L. Our charge density is going to be sigma 2 pi big R. So notice that. That's big R, not little r. That's kind of a big deal because this is where the charge is located versus where your Gaussian cylinder is. So keep track of those r's. As we make this substitution into our equation, we have our left side, we got our right side, the length of the tube ends up canceling out, and sure enough, we're going to end up getting our sigma big R over epsilon naught little r. The key thing is this is over to the r to the 1, right? It's not over r squared. This is an inverse square law. It's just inverse with relation to r. So kind of keep that in mind with cylinders. That'll be different than when we get to spheres in the next video. So what's a little clever trick? I introduced this not because you need to know this necessarily for the AP exam, but it's a really cool kind of symmetry thing that happens that might make everything click for you. If we're just outside the surface R, so here's R, and we're talking about like right outside of it. So I'm calling it R plus. If we plug this into our prior equation, we're going to notice that the R's end up canceling. Where have we seen that before? Yeah? Oh my gosh, it's the same thing as the conducting plates of charge when we're just on the surface of a conducting surface. We've also seen that. Oh my gosh, there he is, that gazelle. We've seen this on the Earth's surface as well, because when we're really, really close to the surface, all these lines are essentially parallel. And that's what we see here. It's saying, hey, it doesn't matter how far away you are. All that matters is the surface charge density divided by our permittivity of a vacuum. And if we get that, we're going to get our electric field. So fun little thing that ends up canceling out that if you're ever on just on the surface of a conductor, you can just treat it like this, no matter what shape it is, because if you're really, really, really close, it's just like you're on the surface of the Earth, which is not flat and is in fact round. So let's look at an example. This example here we have is an insulating cylinder. So once again, because it's an insulator, this makes it a little bit tricky, just because we don't have our E field inside cancel out to 0. It's going to be kind of increasing as we go outwards. So if we look at inside our particular surface, it's going to be 2 pi little r times our L. And our charge enclosed is going to be the density, which was given to us as beta times r. And easy side is done. But on the right side, we now have to get to do some calculus. Hooray! So looking at our tricky side of this equation for Gauss's law, we're looking to plug in our volumetric charge density and our dV term. What is this dV? Well, it's just LdA. How do I get that? Well, I have this tiny little dA element, which represents this little area. Imagine like a ring that has a thin little thickness to it. We'll talk about that here in a second. And I'm stretching it all along this length L. This is what I'm referring to that is capturing some sort of charge within it. So my dA term is going to be this 2 pi r, my circumference, times this tiny little thickness right there, tiny little thickness dr. How does this turn into an area? Well, think of it just being unwound and stretched out to a flat line. This full path would be 2 pi r long, with a thickness of just dr. So really, this is just a rectangle at the very small level. It works out. That's the fun thing about calculus. So when we look at our charge enclosed, we can make this substitution for our LdA, and we end up getting this term. Keep that in mind for what we're going to apply next. Now that we have our charge enclosed, we can then integrate it in terms of r squared. And when we take that one, we have to look at our bounds. When we look at our bounds here, we have to think about what we're integrating from and to. Well, we're looking for the E field where r is less than big R. So we're taking our bounds from 0 out to where r is. This is the region we're looking for. So 0 to r end up being our bounds. When we integrate r squared for our power rule, we get our r cubed over 3. And sure enough, we're going to get this as our charge enclosed for any given radius. This is varying as a function of r, which is the key idea when you solve for the tricky side. So putting this all together, we have our Gauss's law. We have our left side, which was the easy part for our Gaussian surface. That's just the outside surface of our cylinder. And we plugged in our charge enclosed, all that calculus work we did on the previous page. And when we solve this thing through, we see the L's end up canceling, and it goes to this, where we end up having this as a function of r squared. Well, what if we're on the outside of this? I would say it gets easier, and it kind of does. We have our same surface here for our surface area for our Gaussian surface. We're doing that side first. And on the other side, now we're taking the same work we did previously. So when I say it's easier, it's only easier because we already did the work for the interior part. Now we're not integrating to little r, we're integrating to big R. So when we make the same substitution that you would have done before for that calculus work, we're going to get this for our charge enclosed. Putting the two things together, where we plug our area term in and our charge enclosed term in there. When this one cancels out, we get this one where r is greater than r, and this time it's over a little r that's there on the bottom, similar to what we had before, where we have it 1 over r as opposed to 1 over r squared, which we might expect for other shapes. So how do we graph this? What I like to do is plot my bounds first. So I know that at 0, I'm going to have 0 electric field because there's no charge enclosed at 0. I also know at this point, because we solved for it, it's going to be my maximum amount when I'm right located at r. I can find that actually on both these equations. If you plug in r here and you plug in r here, you get the exact same thing, which is a good thing. But what do we do next? Well, to find out how to connect these, we want to use like functional dependence as one option, where let's plug in a halfway point. If I plugged in half r here, half squared gives us 1/4. So my maximum value divided by 4 would put the point right there at the bottom. Well, if I keep the same idea going, r max is right there at that value. If I'm outside of it, if I plug in a 2r, because I'm at r then 2r, that's going to make it be a half. For my functional dependence, the same thing, but just halving it on the bottom. And if I go 4 away, it's going to look like this. So I plug in each of these kind of places to figure out my general locations, and I connect those dots with my nice little smooth curve. And this is what I would expect my electric field sketch to look like for my insulator that had that charge density of beta r. Let's look at one final practice to kind of work this thing through. And this is going to be a coaxial cable, where it has the wire has a linear charge density lambda surrounded by a neutral conducting shell of radius r and an outer radius of 2r. This is what it looks like. And if I kind of do a cutout, imagine this being a cutout of this section kind of superimposed onto this graph. Well, the nice thing is if I look at just the inside for Gauss's law, I know that I'm going to have this Gaussian surface that's located around that dot of 2 pi r times L, and that the total charge enclosed is going to be the linear charge density times the length. Solving for that very quickly, I'm going to find that my E field on the inside region is just going to be lambda over 2 pi epsilon naught r. Doing the same graphing that we did before, at 0, this is going to be undefined. When I'm crazy close to that charge, it's very strong E field. But as I move away to r, it'll turn into r. And if I go half of that distance, I know this is going to end up doubling, because if I'm half the distance, it'll double. So I kind of get these 2 points that exist. But also remember, when I'm inside of a conductor, what do I know the electric field is going to be? Yeah, just 0. And if I continue my trend, kind of plugging in variances on that one, if I plug up to 3r or 2r there at the middle, I'm going to get half. And then 4, I'm going to get way yonder over there, plugging a 4 on the bottom. And sure enough, the graph's going to look something like this, where it's going to be decaying down at a 1 over r rate. But when I get to the conductor, it's going to drop out and go to 0 because the electric field inside of a conductor is always 0. So what should we take away from this video for our cylindrically symmetric surfaces? The main thing is if it's conductor, it's going to be 0. Don't forget that. But if you're close to that surface, you can almost treat it as though this crazy shape, whether it's a cylinder or a sphere, whatever it might be, that it was a plane surface. It's a fun little shortcut. Don't forget the left side of Gauss's law is the easy side due to symmetry. And if you're dealing with a Gaussian cylinder, it's always going to be that 2 pi r L kind of term that pops up there. But here's what I'm going to point out. You could memorize how you do all the dVs for integrals and cylinders and how to work it through, but you're better off if you actually memorize the process, because if you know geometrically in your mind how these things are being built, it'll make a lot more sense when you're solving a problem versus kind of plugging things in these preset equations that you may have memorized. And besides, you oftentimes have to show that work on the AP exam to earn full credit. So with that said, I want to thank you guys for stopping by, and we'll see you in the next video. So long.